first speaker is Dr. Heng Xiao from Virginia Tech. He used to be my colleague, and he is currently an associate professor in Virginia Tech. And prior to Virginia Tech employment, he was a postdoctoral researcher in ETH Zurich in Switzerland. And he had his PhD from Princeton, and then master's from KTH, and he had bachelor's from China Zhejiang University. Okay, with that, go ahead, Heng.
Can you hear me okay?
Yes, perfect.
Okay, yeah. Dr. Choi, thank you for your introduction, and very nice to see you and see our audience. Today, I'm going to share recent work in ensemble-based learning of turbulence models from sparse data. And this is kind of a slight departure from what I have been doing in machine learning in the past few years. So specifically, it's a unified perspective of data assimilation and machine learning. So my talk is going to be on learning models, but I think I want to revisit what I've been doing in data assimilation some years ago, because I'm borrowing a lot of basically the ideas from there. So just for the audience who are not familiar with turbulent flows, turbulence is a ubiquitous phenomenon in natural and industrial flows, as you can see here. I happen to be in the aerospace and ocean engineering department, so I put waves and aircraft here, but in chemical engineering, mechanical engineering, there are many places. Specifically in aerospace engineering, RANS or Reynolds average Navier-Stokes are still the workhorse tool in industrial CFD. This is because high fidelity models such as large area simulation and direct and numerical simulations are still too expensive. But even though the RANS models are widely used, it has poor performances for many flows, many practical flows, such as flows with separation, pressure gradient, and flow curvature. So we need to quantify and reduce the model uncertainties in these models. And we choose to use data-driven method combined with physical constraint to tackle this challenge. So again, this is for students who are not in this field yet. So you probably have seen the incompressible Navier-Stokes equations, which consist of mass conservation equation and momentum conservation. This can be solved, but solving this accurately would need to resolve a very large range of scales, up to millions of or hundreds of millions of difference of between the largest and the smallest scale, and the computational cost in terms of the mesh is very expensive. So as a result, typically you can do a Reynolds decomposition to decompose the instantaneous velocity and pressure into mean component and fluctuation component, and you can plug it back to do a Reynolds averaging. That's basically take the long time averaging or ensemble averaging. Now, after doing that, for most of the terms, because they are linear, the fluctuation component have zero mean, so they just disappear. Except that there's a term that is the convection term that end up with the covariance of the fluctuations, and this is basically the source of the uncertainty in RANS models. So the good news is that you can derive a transport PDE for this equation, which is a tensorial PDE, but the PDE itself contains even more closed terms, so it's a closure problem. Now, back in about 5 or 6 years ago, we did some work in using data to reduce the model uncertainties here. That is injecting uncertainties in the Reynolds stress field. So tau is our Reynolds stress field, and we know that the uncertainty is there. Okay, what we do is we will represent it. We will somehow parameterize that Reynolds stress field, and then we'll draw samples from this random field. Basically, each Reynolds stress, possible Reynolds stress, is a sample of of a random field, and then for each of the random stress field you draw from these distributions, you can propagate it. Basically, you plug it into a run solver, and you'll be able to obtain the velocities and other observable quantities. And then you can bring data. Suppose if you have some data in this system, some maybe sparse data, you can bring in the observation data to obtain the posterior. So this is basically a typical Bayesian analysis. And based on that analysis, you'll be able to update the coefficients that you use to parameterize the renal stress. Okay, so the takeaway message is that this data assimilation method is essentially using small amounts of observation data to infer a field. In this case, is the renal stress field, which is a very large, very high dimension field. Okay? But in the end, what you do is you are doing an update. Basically, omega is your coefficients. Next step is equal to current step plus correction, and that correction depends on the difference between your observation data and your predicted data. Let's say drag coefficient. If y is the drag coefficient, and then h is the run solver and observation operator. You solve for run. You take renal stress. You solve for the velocity, and then you observe and to obtain the drag. Okay? So essentially, this is an update, and you will see that if you know machine learning, this is very similar to what you see in machine learning in terms of the gradient descent. Yeah? So we did bring some physics, that is the renal stress at each step. You can decompose it to the magnitude, which is the turbulent kinetic energy, and C and eta indicate the aspect ratio. If you think of it as an ellipsoid, okay, and phi1, phi2, phi3 are the orientation of the tensor. Okay? And specifically, if you take that aspect ratio, you can map it to a triangle. Either this is a barycentric triangle, but it's the same as a nonlinear triangle. And you can use this physical constraint to constrain your perturbations. And this is called realizability constraint. But of course, you could also invoke constraint in terms of the field. Yeah? In addition to the fact that at each point, the renal stress must be realizable, your field needs to have some smoothness. So what we do is we model the renal stress field anisotropy as a Gaussian random field with a covariance structure. And then we use the Ryan's prediction as the mean. This is your best guess, basically. And then you will do a Cahulan-Love expansion to represent it in terms of the mode. So this is the same as the POD modes that a lot of you are familiar with in the fluid dynamics community. So you can think these are the first, second, third modes, but these modes are specified. There's no physical basis for that. But because of the decomposition, you decompose the renal stress field into a number of coefficients, and then you can infer the coefficients. Now, I'll show some results. So this is a periodic hill. Basically, the flow goes from left to right, and there's a separation zone here. And you can see that on the right figure, the black is the direct numerical simulation data, which is the truth. And then the baseline runs in a K-epsilon model. This is the red line. And then if you perturb the renal stress and sample it, and then for each of the renal stress, you get a velocity, and then these are indicated as a green lines, gray lines. Okay? So you can see they deviate quite significantly, particularly in the region that is in the separation zone. Now, suppose if you have observation data, velocity data at the points indicated as a black cross, you'll see that you'll be able to very much correct it. This is the data assimilation procedure. And after the correction in the posterior, you can see that the samples, each of the samples agree with the DNS data much better, particularly in the recirculation zone. Of course, it's not surprising that you have better agreement in the in the regions that you have data. But even in this region, we do not have observation data. Because of the covariance between the velocities in these locations, we were able to improve the velocities here. But remember that we don't modify the velocity field. We respect the constraint on the velocity field, and we only correct the underlying Reynolds stress or Reynolds stress anisotropy. And this is another case that is the square dark, the flow goes along the pipe, and because of the Reynolds stress and imbalance, you have in-plane velocities, as you can see here. And in this case, we look at the in-plane velocity. On the left is the posterior. You can see there's quite a lot of scatter, and the baseline model basically cannot capture the in-plane velocity at all. Now, once you add the sparse velocity observation, you're observing at 0.5, and you can see that at all the stations, it has been improved, the velocity. Okay? So these are, I think it's interesting that you can use some observation data to improve the full field predictions, but this only really works for system monitoring. If you are talking about a simulation of the weather or the F, you only have one system and you have quite some data, right? And the data actually comes in continuously, streaming online. But in a lot of cases in aerospace engineering, you need to do design analysis and optimization. Okay? In these cases, you have to explore the design space. So you have to evaluate thousands of candidate designs where you don't have even have built the model yet. Where do you get the data? You don't. Yeah. But in this case, sometimes you do have full field data, which we have worked on this scenario for some time. But it could be that you don't have full field data. You only have some spontaneous sparse data. Yeah. But the task here is that you can learn in one flow, but you are required to extrapolate or predict flows that are possibly similar but different from the flow that you have data from. Yeah. So that's the basic assumption. I want to point out to the early work of Lin and others. So basically, she derived based on the Pope's generalized eddy viscosity model. She decomposed the Reynolds anisotropy in terms of a tensorial basis and learned the basis. And this is the so-called TBN tensorial basis neural network. This is very flexible model, and it has all the invariance guaranteed, but you need DNS data and high quality experimental data, which is very difficult to come by. Now, recently we have learned, we have worked on a so-called a non-local Reynolds stress model, because you know that even though this is a very generalized model, it's still a local model. The Reynolds stress anisotropy still only depends on the stream rate at a particular point, at that point. But in general, this is not true. You need to have a long local dependence, and I will refer to our recent publication where you can learn a model that is velocity, the Reynolds stress at one point, okay, as indicated as red, depends on the stream rate at a bunch of points, these blue points, and we call it a cloud of points. And we can ensure translation, Galilean, and rotation invariance, as well as permutation invariance. That is, it doesn't matter how you number your points. The learn function is invariant. Okay. Now, but what if we only have sparse data? Now we're back to our the first part of my talk. You only have observation data at a bunch of points, or maybe you may have a drag, lift, and so on. Okay. How do you learn a model? Is it possible? Well, it turns out that if you take a unified perspective, it's not that different from data simulation. Now, the aerospace engineering community have been doing adjoint optimization for years. Here, you can basically tune the parameter, right? The parameter in the model such that your prediction agree with the very sparse observations. Let's say you want to agree with the velocity observations, and you try to tune the model beta, yeah? The model parameter beta. In data simulation, we make it more general. That is, we're not tuning the model parameter, we're tuning well, we are correcting the Reynolds stress field itself, even though, of course, we are not tuning the cell by cell, we're tuning the mode coefficient, but it's the same. You could also tune cell by cell and enforce some smoothness and continuity. But in machine learning, this is not so different. In machine learning, you could basically represent the turbulence model with a neural network, like what I described, a non-local VCN or the TBN of Julia Lin. And then you represent this neural network turbulence model with a neural network W. You tune the W such that your prediction agree with your model. So it's just a very extremely flexible model. What's the difference between the adjoint tuning of beta and the tuning of the machine learning? Well, the difference is that the W in the machine learning is thousands or even millions of degree of freedom. It's extremely over-parameterized model, but the idea is the same. So we tried two things. One is, can we just combine machine learning and adjoint? Okay? So we represent the turbulence model with a neural network, and we embed this into a RAN solver. Okay. So now my question is, how do we optimize the model W so that our object function J is minimized? Well, gradient descent. You need the gradient of J with respect to W, and that it can be obtained by chain rule. That is, what's J with respect to tau, which is Reynolds stress, and what is the derivative of Reynolds stress with respect to W? Well, here you can just do back propagation, because the neural network is extremely cheap to obtain the sensitivity or the gradient. Well, to get this part, dj, d tau, you need to do adjoint solver, and this is a bit expensive, but this has been done for years in aerospace engineering. Okay? So that's our recent work that is published in TML. Now, alternative approach would be, can we just use a data assimilation method, the ENKF ensemble common filtering, that you can, here is the same framework, except that you are not representing, parameterizing the Reynolds stress. You are parameterizing a model that map the mean field U to the Reynolds stress tau. So as you can see here, there's a mapping from U to tau and parameterized by a network, and I tune this. And then for each of the model W, we map to different taus, okay? And for each of the tau, I'm going to propagate to the velocity, and then I'll do the same so-called analysis or innovation to update the weights of the neural network, which is now our state. Before it was the Reynolds stress values at each cell. Now it's the weight of the neural network that is representing our model. So I put it here. Is essentially a different objective functions. In the direct learning of Julia Lin, your cost function is the Reynolds stress data tau, and you're doing this update within gradient descent or maybe stochastic gradient descent. In the neural network plus adjoint, this is what we did. We are doing very similar thing, except that the gradient has to be the gradient has to be computed with a chain rule. Okay? Now in ensemble learning, this is the same as I recalled in the beginning of the talk. That is, you're updating that by using a correction, and this is called common correction. Common is computed here from the ensembles, and Y plus H is the discrepancy in the observation space. That is the difference in terms of the velocity observations at that few locations that you observe. Okay? So again, I'm invoking this flow, which is a very classical flow in turbulence modeling. Now, in this case, I'm learning a model that is known. So we know this model, but we don't tell it to the procedure. And you can see that there are analytical expressions here, and you can see that the choose is the black, and the K epsilon, of course, is just a fixed coefficient, 0.09. And you may recognize that. And the adjoint on ensemble indicator is in green and blue. And you can see they pretty much mostly agree, except here, the departure is quite dramatic. That means this part of the function space is not learned very well. Why is that? Well, this is because in our case, in this case, the small theta part does not have any representation. This is the prediction and the truth, the so-called validation plot. As you can see, most of the theta here are focused on between 5 and 8, and the small theta region does not have that much of representation. That is, it's not covered from, so you cannot learn this part from this case. But if you enrich your data set, you will be able to learn this part. But that said, it doesn't, if you're only interested in this kind of flows, this set of flows, you don't need to care about this small part because it doesn't occur in this flow. And you can see here the ground truth. If we look at the Reynolds stress and the imbalance of the Reynolds stress, which is directly informed by the in-plane velocities, as you can see, they're all very similar in the adjoint-based, and you can learn this very well. Ensemble-based, and you can learn it equally well. So I think this is something is worth noting. But I do want to draw a comparison between the two methods. That is, the statistical calculation is very cheap. Most of the CPU time is spent on the run solver because in order to learn from sparse data, you need the run solver, okay? Because you need to propagate the Reynolds stress, okay, which is your model output, through the run solver to get the observable quantities such as velocity, pressure, drag, and lift, and so on. So most of the time is spent on here. And it runs in ensemble method, you run the ensemble of the simulations. So for example, we typically use 60 samples on 60 cores. So it's embarrassingly parallel. You can run this at the same time without any communication. You communicate it only after you are done with the simulation. And we can see that the ensemble method is for CPU time per step is very similar, 8 minutes versus 7 minutes, but it only takes 50 steps to converge. This is because we use the Heng information. In the ensemble method, you have Heng information, which is the second order derivative, which can massively accelerate the convergence. While the neural network converges a lot slower, and it needs a solver adjoint and the primal as well. So instead, as a result, the wartime ensemble method 6 hours, and the adjoint is like a week almost. It's pretty expensive. So, so what about the extrapolation? And if you train on this on one flow and predict on another, well, we trained on 1.0, and then you can see that it can predict in other the slopes like 0.8 and 1.5, which is put it on the left and the right. And then the discrepancies you can see here, the baseline model is overall is 10%, and here, and the learned model performs much better. But particularly in the recirculation region, the learned model has a significant improvement across the board almost, and except for 0.5, which is a very challenging case. Well, that said, I think the basic idea is that we can combine ideas from ensemble-based data assimilation, specifically ensemble common filtering and the variant method, and adjoint method from the aerospace engineering and machine learning to learn turbulence models and really all other models. The ensemble-based learning method is competitive in modern learning from sparse data because of the non-intrusiveness of the solver. You don't need to change anything. You don't need to derive an adjoint. You just run the ensemble simulation and perform statistical analysis to learn the model. So with that, I thank you for your attention, and I will be happy to take any questions.
Oh, sorry.
Oh, yeah. So yeah, now is a Q&A time. So I'm going to. So hi, Heng. It's good to see you again in the Zoom meeting. So I have one question. It's kind of general question. So you have a quite long experience in applying machine learning for improving a turbulence model and to get a better prediction in the flow field. And you also changed some geometry from your training data set to the test data, and so I'm just curious from your experience, if you have a completely new geometry, then is this kind of machine learning technique to train a turbulence model or to get a better representation of the Reynolds stress or something else, then do you think that is still applicable?
I think you would have to see some kind of form of the flow, not exactly the same as you can see it in the periodic Hill, parameterized the periodic Hill case. You can say you can learn from 1.0, extrapolate to quite far, 1.5 or 0.8, but when you get to very low, like in 0.5, it's very steep, then you are going to run into some new physics that you have not accounted for before. And I doubt that any learning would be able to figure that out. But that said, so you know that in aerospace engineering, you have this wind body juncture, right? It's a very challenging flow, and almost no model can predict it well. But you don't have to have exactly the same geometry to learn. You could have a square dot, right? This is the secondary flow, which is very similar to the corner flow in the wind body juncture. So, and then you could have boundary layer, and you could have a flat plate and adverse pressure gradient or favorable pressure gradient, all kinds of elements put together. I think it's possible to predict a more complex flow. But if you have not seen one particular kind of physics altogether, if this physics is missing altogether in your model, then I don't think it would. Machine learning is not magic. It's just, I mean, I think I recall remind everybody in the audience that is essentially machine learning is just the optimization, right? So you have a objective function, right? And then you are trying to reduce the objective function by tuning your weights. Right? That's what it is.
All right, thank you, Heng. By the way, this was a Soigun-ji.
I have recognized your voice. I couldn't see your camera, but yeah.
Right. Okay. Any other questions from audience online? You've been very quiet. What about people from the floor? No? Okay, Heng, my last question. So Dr. G was talking about, the generality over varying shape, right? But if flow Reynolds number changes, so we have to learn the flow all from the beginning, right?
Well, it depends on how in turbulent flows, depend on how the Reynolds number effects come in, right? I don't know. In very high Reynolds numbers, it looks like the Reynolds number is not significant. So it really depends on the physics. In my opinion, I don't know what you mean by Reynolds number. Is it going from 10,000 to 100,000, or is it going from 100 to 5,000? Right, depends on how you are, how much the changes. That's what I can.
So let's say that you are changing your Reynolds number from 100 to 500 or 1,000. Yeah. So how what's happening? So should we do all the calculation and learn the model again?
Hard to say. I mean, because we often have a much higher Reynolds number, and the Reynolds number effect is not so significant.
Right.
We mostly have let's say pressure gradient. If you have let's say if you have a flow that here you have the separation, right? If your training data do not have any flow that has a separation, and then you probably are not going to do it, right? So I guess you have to have somewhat seen that kind of physics in your training data.
Okay. Okay. Thanks a lot, Heng.